All right, I wanted to make a quick video on how we might find the net force acting on a charge when you have a group of charges. So this is going to be doing two things. You'll be reviewing how to add vectors, which you learned last semester, but you probably need to brush up on it. And you'll be using this new concept of the Coulomb force, which is the force that exists between two charges. Keeping in mind, this is the expression here for the Coulomb force, where K is roughly 9 times 10 to the 9th. And then the force between charges is proportional to the two charges involved, their magnitudes, and it's inversely proportional to the square of the distance between them. Now, the force between two charges can either be attractive or repulsive, because we know opposites attract and like charges repel. And that's where something tricky happens when we're doing a problem like this, because the first thing we're going to do is we're going to draw vectors on our diagram to represent the force that this 3 microcoulomb charge feels due to each of the 3 other charges. And we'll use the fact of whether, when we're thinking about a pair of charges, would they attract the 3 microcoulomb charge or repel it, and use that to draw the force in the correct direction. Then we'll be able to get into the adding of the vectors. So I'm going to try to use a unique color for the force. So let's go through all 3 of the charges and how they would exert a force on the charge number 2, which has a charge of 3 microcoulombs and it's positive. So first, if I look at charge number 1 is negative. It has a charge of minus 5 microcoulombs. And so it is going to attract charge number 2. And so that means that it's going to exert a force to the left. So I'm going to draw it like this. It's a force on charge 2. I'm going to label it force 1 because it's the force caused by charge 1. Now I'm going to go to charge 3. Charge 3 is also negative, and when I think about the force that it'll exert on charge number 2, the positive 3 microcoulomb force, a charge, is also going to attract it. So it's going to be a force along the line that joins the two charges, so it'll look like that, and I'm going to call this F3. Finally, we're going to think about what is the force that charge number 4 exerts on charge number 2. Now, in this situation, both of the charges are positive, so the 4 microcoulomb charge is going to repel it. So that force is going to be up, indicating repulsion, and I'm going to call that F4. All right, so now I've drawn the direction of the 3 forces that I have to add. I've already taken into account the sign of the charges, so when I'm calculating how large these forces are, when I'm finding their magnitudes, I'm going to ignore the sign, okay? I'm going to say that one more time. Because I already used the signs of the charges to draw the direction of the force, I do not need to use the negative or positive signs in the calculation of the magnitude. All right, so keeping in mind what I'm doing is I'm finding the resultant force, which is adding F1 plus F3 plus F4. Now the way that I want to do that is I want to find the x component. So I have F1x plus F3x plus F4x, and I also am going to find the y component of the resultant force, which is going to be found by taking the individual y components. Now, before I do that, I need to know how big each of these forces are. So I'm going to find their magnitude. I'm going to use this expression to do the calculation. So for force 1, I'm going to use K, so 9 times 10 to the 9th, then times charge number 1 times charge number 2. So I'm going to do 5 microcoulombs. A microcoulomb is 10 to the minus 6 times 3 microcoulombs, and then the distance between them is 0.3 meters squared. And so when I calculate that out, that ends up to be a force of 1.5 newtons. So now I know how big it is. Let's do F3. I get 9 times 10 to the 9th. Now the two charges I'm talking about are charge number 3 and charge number 2. So we get 2 microcoulombs and 3 microcoulombs. The distance between these two is going to be 0.5 meters. You can use the Pythagorean theorem to check that out. And so I find that the magnitude of this force is 0.216. It's a little smaller. The two charges are further apart, and they have smaller magnitudes. So it makes sense. Finally, force 4, I'm going to be using charge number 4, charge number 2. And the distance between those is 0.4 meters. And that ends up to be 0.675. So all of these are the magnitudes of the forces. Now, when I want to find the x components, the total x components, so I'm going to be looking at the x component of F1. Well, F1 is totally in the x direction, so this is just minus 1.5. Now I'm using my picture to give the correct sign to these components. Because F1 pointed to the left, I make it negative. F3 is also negative. It's going to be equal to F3, 0.216, and then times the cosine of theta. And we're going to look at what that angle is in a minute. And then finally, the x component of F4. Well, F4 is straight up. It doesn't have an x component. So my total x component of my resultant force ends up to be 1.63 newtons. Now, just as an aside, how would I find this angle theta? I'm just going to do it right here. I could say that the tangent of theta is equal to the opposite, which is 0.4 meters over the adjacent side. And if I take the inverse tangent of that, I get an angle is 53.1 degrees. So now you know what that angle is. So I have to find my y component of my resultant vector. So it's F1y. Now that one is 0 because F1 was to the left. The y component of F3 is 0.216 times the sine of theta. Remember, theta was a 53.1. And then the y component of F4, well, F4 is totally in the y direction, so I just write 0.675. And this ends up to be 0.502 newtons. All right? So hopefully this is looking familiar, that you still have, a rusty memory of how to add vectors, because we still need to know how to do it. Keep in mind, now that I found the x component and the y component of my resultant vector, I use the Pythagorean theorem to calculate the magnitude, and I get 1.71 newtons. And then I'm going to find the angle. I'm going to call that angle beta, just to differentiate it from my other angle. So this is the angle that the resultant vector will be pointing in. It's going to be given by the inverse tangent of the y component over the x component. So it's the inverse tangent of 0.502 over 1.63 negative. I do have to put that negative in there. I end up getting a beta, when I do my calculator, is minus 17.1 degrees. Now I have to think about what quadrant this force would be in. It has a negative x component and a positive y component. So, roughly, this is FR, negative x component, positive y component. So the way that I would use this is that the angle it makes us is going to be 180 minus 17.1 degrees. And so this roughly means it's about 163 degrees from the positive x-axis. All right, hope that helps. The positive x-axis